Okay, so let's talk Fibonacci numbers. Once again, this is another video of Code Made Easy series by Zindua School. So Fibonacci numbers are interesting because they are one of the easiest ways to learn recursion in programming. So let's look at this series over here. So we have 1 as the first one, we have 1 as the second term in our series, and then we have this 2. So what you'll realize in Fibonacci numbers is the next term is a sum of the previous two numbers. Apart from the first two where you just define, the rest are going to be that. So if this 2 is going to be 1 plus 1, this 3 is going to be 2 plus 1, this 5 is going to be 3 plus 2, and so on and so forth. So in short, we can easily summarize Fibonacci numbers with like an objective function, where we go ahead and say Fn, which is like Fibonacci of n, is always going to be equal to f of n minus 1 plus f of n minus 2. Just as simple as that. That's how we compute the nth number in a Fibonacci series, right? Regardless of how long this is. And that's how we'd actually do it in code, right? If we were to implement Fibonacci numbers in code, we literally come in and say, define the function Fibonacci, and this is now a recursive function, a function that calls itself, and we just tell it to return Fibonacci of n minus 1 plus Fibonacci of n minus 2. The code is going to recursively call itself up until it gets to the answer. But now there's a problem. We can't call the previous two terms when we are on the first term or the second term. So we need to go ahead and add our base cases, and here we're going to add them like this. So if n is less than 0, we'll return nothing. However, if our n is equal to 1 or equal to 2, then we'll return 1. And then from then on, we can recursively compute this particular number. That's how we do Fibonacci series, right? And here we can see our 10th term was 55. So if I run this code really, really fast, I get 55. But we have a problem here. The problem with recursion is we are recalling the function, we might have a particular problem that affects performance. And we can see it when we start computing for a number as large as 30. And now all of a sudden, we are seeing some time that's being taken here. Or probably let's do 100. And now all of a sudden, we can't get our response in the right amount of time. So what should be our solution here? Or let's understand and diagnose the problem. When you think of Fibonacci series, this is the graph that comes to life. So first of all, if I do Fibonacci of 6, it has to call Fibonacci of 5, Fibonacci of 4. When it calls Fibonacci of 5, it has to call 4 and 3. So this is the recursion tree that we are able to see for that Fibonacci of 6 to be computed. And there's a key problem here. When I'm doing Fibonacci of 4 here, it's also recomputed on this other end. When I'm doing Fibonacci of 3 here, you can see there's those repetitive computations that happen. And this tree, when our number becomes really, really large, the amount of times where we have this sort of repetitions is going to be extremely huge. So this is just Fibonacci of 6. If we were supposed to do Fibonacci of 7, it would mean we need to have this entire tree for Fibonacci of 5 on this other front to be able to compute Fibonacci of 7. And now you start seeing how this tree could easily multiply to such a big tree when we are at Fibonacci of 100. So this is what we call like a big O complexity of O to the power n, right? Where the number of operations is doubling for every unit increment of n. And that tends to be very exponential, and it doesn't work for large numbers. That's why it's hard to compute Fibonacci of 100. The solution to this is pretty simple. What if we avoid the recomputations by just saving an answer whenever we compute it? And that's why in my second code solution here, right? So here we can do 10 really easily. We can't do 100. So now in my solution, I'm going to introduce a cache here where I am going to store the previously computed numbers. And now after my base cases, I'm going to check whether this n is in my dictionary. So if it's in my cache.keys, then I will return the response from that particular dictionary. If it's not, I will compute. Keep in mind, this was my recursive subproblem there. So I will recompute it, save it in my dictionary, then return the response there. This way we avoid repetitive computations. And now when I do Fibonacci of 100, all of a sudden we can get this answer in seconds, which is not the same thing we could get there. And that's how we optimize recursive functions with caching. And this concept is called dynamic programming. If you want to learn more about dynamic programming, and more advanced algorithms, check out the Data Structures and Algorithms course by Zindua School and Career Kickstart, where we delve deeper into more algorithms and such problems.